Hello, everyone. I'm Ren. Today, I'm going to present our work aware in automating workload autoscaling with reinforcement learning in production cloud systems. This work is in collaboration with IBM Research. Cloud systems are a natural arena for reinforcement learning or RL for several reasons. First, they are full of sequential decision-making process in various cloud system management tasks. Examples include resource management, which is everywhere in computer systems across different layers in the hierarchy. And other examples include job scheduling or congestion control, etc. Such problems are usually well-defined and they have been around for a long time, but yet remain significantly challenging. The main reason is that these problems are hard to model due to dynamicity in applications and systems. Existing approaches are mainly relying on human-engineered heuristics or static policies. IO, which represents a popular category of online learning-based approaches, enables us to use deep neural networks or DNNs to express the complex dynamics with raw and noisy signals. And they can also be used to represent policies without relying on any inaccurate assumptions, such as the system models. And training such deep neural networks might be data hungry, but fortunately, thanks to rich monitoring infrastructure, there have been abundant data generated in modern cloud systems, which consist of real-time monitoring measurements, time series system metrics, and workload performance, etc. For example, in Kubernetes and OpenShift, we have Prometheus, and in production cloud data centers, examples include Google's Monarch system or Meta's Scuba system, etc. Actually, there have been a large body of work in academia modeling various system management tasks using an IO formulation, training the agent to learn the optimal policy, and showing that the IO-based approach performs better in each system task. Examples include cluster management, scheduling, networking, database optimization, and cluster resource management like resource autoscaling. And in this work, I'm going to focus on resource autoscaling as a concrete example of cluster resource management. As a primer, in I/O, the system task is modeled as a Markov decision process. An artificial agent is created to interact with the environment in a step-by-step fashion. At each time step T, it's going to take observation or state as T and make an action AT and then receive the reward RT. The reward indicates the performance of the agent or how good the learned policy is given the current context or states of the environment. And the IO agent is designed and trained to optimize for specific workloads experienced in the cloud systems environment. For example, it could be small jobs, low load, periodicity, or high scaling factor, etc. And the IO agent will continuously to learn by maximizing the expected cumulative reward in a trajectory with T steps. There are two stages in the IO agent lifecycle, policy training and policy serving. During policy training, the model parameters are continuously being updated, and after convergence, the trained model are used for inference. We call it policy serving stage. And the reward is aligned with the objectives, such as to meet application or system service level objectives or SLOs, or to keep the cluster utilization at a high level. However, there is still a gap to bridge the advances in IO modeling and algorithms to production systems. And moreover, a framework is needed to enable robust and reliable deployment of IO-based controllers in real systems. So to deliver such a framework for managing and running IO-based controllers in production cloud systems, we took the example of multidimensional workload autoscaling in Kubernetes. In a Kubernetes cluster, application workloads are deployed as pods or containers in order to continuously meet application SLOs and achieve high resource utilization. The IO-based autoscaler is responsible for both vertical scaling, which is to resize the container in CPU or memory, and horizontal scaling, which is to adjust the number of replicas or containers. However, we have identified that there are three main challenges when porting IO-based solutions in production, and to enable built-in intelligence in cloud systems with less manual intervention while achieving high robustness and self-adaptation in both policy training and policy serving. First, in early stages of our training, the agent tends to generate poor auto-scaling decisions, which lead to lower than baseline reward. This is due to IO exploration. Compared to converged IO policy, the CPU and memory utilization deficit can be up to 42% and 30%. We found that it is basically due to over-provisioning. And there can also be more SLO violations because the policy is not able to rescale the resources properly for workload changes. And to tackle this, in our solution, we allow reliable IO exploration with offline training, or we call it bootstrapping, in combination with online training and inference. And the benefit is essentially significantly higher reward, illustrated in the blue shaded area, compared to the baseline IO agent firm in red. And the second challenge is that during policy serving stage, the IO agent performance degrades when workloads are updated. Examples include file or table size changes, machine learning model updates, image dimension changes, or load is simply changed from low to high or high to low, etc. In our experiment, we found that these changes may result in up to 21.8% reward drops in percentage. We proposed a solution which is to continuously monitor and retraining detection and trigger in the policy serving stage. Moreover, the trained IO policy are application specific, and it is costly to adapt to new applications. We found that in our experiment, there can be 45% reward degradation and more than 200 episodes of retraining when adapting to new applications. To provide fast model adaptation, we propose to leverage meta-learning in our solution. So to combine our solutions from these findings for each of these challenges, we designed and implemented Aware, which has the following 4 key components. First, we have a multi-dimensional pod autoscaling system in Kubernetes for IO, which constructs the IO environments by wrapping up matrix collection and scaling actions actuation. And secondly, we have an IO bootstrapper that combines offline and online training. In the online mode, the IO agent directly interacts with the IO environment through an API. And during the offline mode, the bootstrapper intercepts the interaction with the API by taking the scaling actions from the default vertical and horizontal autoscalers, VPA and HPA, given the observed matrix. And the state action trajectories are then stored in a database. The IO agent will treat this database as a replay buffer for policy training in an offline fashion. And next, we have IO retraining detection and trigger module by continuously monitoring recent rewards and switching between the policy training and policy serving modes based on the user-specified objectives. And lastly, we have a meta-learning module for fast model adaptation. The key idea here is to model the IO agent as a base learner and create a meta-learner to learn to generate embeddings that can precisely differentiate and represent each individual applications. So now let's first look at MPA. MPA is an open source framework that allows general workloads on Kubernetes to use IO-based autoscalers such as Firm. And MPA allows us to reuse VPA and HPA as a fallback to IO to have a default autoscaling algorithm. For application deployments in Kubernetes, HPA obtains metrics such as utilizations from the metrics server, and then adjusts the number of replicas to meet that utilization or the performance metric threshold. And VPA has a custom resource definition, or CRD, on scaling specs and status, and then creates 3 controllers. The recommender controller sets the scaling recommendations based on the observed metrics, and the VPA animation controller and the updater watch the VPA CR object to set the vertical scaling configurations. The design of MPA follows the similar style of VPA that separates scaling recommendation from actuation, which supports customized plug-and-play multidimensional autoscaling algorithms such as IO. In more detail, we have application deployments and metric servers in Kubernetes cluster, and the MPA recommender gets the measurements from the metric server and gets the scaling recommendations from either the IO controller or the default VPA or HPA. The recommender then sets the scaling configurations in MPA API. Then the updater operator executes any horizontal scaling configuration updates, and accordingly, the animation controller executes any vertical scaling configuration updates. MPA module enables like step-by-step interaction with the environment for IO training. Then let's look at how IO bootstrapping combines offline and online training. After initialization, the IO agent will enter offline training stage first by default, unless the user skips this step explicitly. In the offline training mode, the VP and HPA autoscalers will be used to interact with the API, setting scaling configurations at runtime. And meanwhile, the IO agent is being trained by drawing trajectories from the database. When the reward of the offline trained IO meets a user-specified threshold, the training will be switched to online, where the agent will directly interact with the environment. And the rewards obtained by the agent are continuously being monitored and compared to the threshold for the average and the standard deviation. If the rewards fluctuate a lot, or the average reward is lower than a user-defined threshold, this indicates a non-convergence, and the model training will continue, and the IO policy will still be updated. And lastly, let's address the model adaptation challenge with meta-learning. The goal is to reduce IO model training time and adapt quickly to new application workloads, which can be unseen during training. Our key idea is to model each agent as a base learner, and then create a meta learner to learn to generate an embedding that can accurately represent each environment. The embedding is then fed to the base learner as the input of the state, and the learned policy is essentially conditioned on this embedding, so the policy can be customized to specific application workload environment. Meta learning is known as like learning to learn, which is capable of generalizing to new environments that have never been encountered during training. The adaptation process essentially require like a limited exposure to the new application environment, essentially a mini training session. It provides a systematic framework that automatically adjusts hidden states to learn, compared to ad hoc classification first and then training one policy per cluster. In Aware, as I mentioned, that our agent is modeled as a base learner. So this figure shows that, which takes the states and generate the actions for the scaling recommendations. And then we create a meta learner. The IO trajectories from the base learner, like interacting with each environment, it represents the application workload as well, are collected. And the meta learner then takes a bunch of trajectories from the same application as the input. We leverage a bidirectional RNN to generate the embedding, given the input, encoding the behavior of the IO agent in managing the workloads, because it includes the states, actions, and rewards at each time step. The embedding is then fed to the base learner as part of the state input. So what does this embedding mean? Let's look at this from a systems perspective. The embedding essentially encodes both spatial and temporal characteristics of the application workloads. And why is that? This is because for different applications, the same scaling action might lead to different states, for example, different latency or different resource utilization. These are included in trajectories as states, actions, or reward. For example, it can be shown as heat maps where darker color indicates worse performance given the same resource allocation. And in the projected vector space, each embedding from one environment is a dot. Applications with similar characteristics are then projected to adjacent locations, while applications with quite different behaviors are projected to locations that are far away from each other. The embedding also captures temporal characteristics because the trajectory also includes time series information as well. For example, the arrival rate per time step or the utilization traces. Similarly, applications with very similar load variation patterns are projected to adjacent locations. And in the evaluation, we are interested in the three main questions. Does Aware provide fast model adaptation to new workloads, essentially to understand the value of meta-learning? And how does Aware perform in online policy serving during workload changes? And lastly, how does Aware perform in the early stage of policy training compared to no bootstrapping? In the evaluation, we adopted 16 representative serverless workloads, like function segments, because serverless workloads typically require dynamic autoscaling. And then we generated 1,000 synthetic applications by randomly selecting and combining segments from the pool. We adopted the IO agent implementation from Firm which uses DDPJ, an actor critique array algorithm. The reward function basically consists of two parts. It gives high reward to higher resource utilizations and high SLO preservation ratios. So when training or retraining the IO model for new application workloads, we found that Aware adapts 5.5 times and 5 times faster than transfer learning, and then 4.6 times faster than transfer learning with additional attributes. And those attributes include information like the map of performance sensitivity to resource allocation changes. And during retraining, Aware saves up to 72% CPU cycles and reduces CPU and memory utilization deficit by 4.6 times and 6.2 times because of faster convergence. And last but not least, Aware reduces SLO violations by 7.1 times. In the evaluation of bootstrapping, Aware had 47% and 32% higher CPU and memory utilization. It reduced SLO violations by 16.9 times compared to firm without bootstrapping. In the evaluation of policy serving performance online, Aware had 9% and 14% higher CPU and memory utilization. It reduced the SLO violations by 3 times compared to firm without retraining monitoring and triggering. So in conclusion, we have proposed firm like Aware, which is a extensible framework for deploying and managing IO-based controllers in production systems. Aware provides fast adaptation with meta-learning, reliable IO exploration with bootstrapping, and robust online performance with timely retraining. We have then demonstrated Aware in the task of workload autoscaling, and the evaluation results show that Aware adapts a learned policy to new workloads by 5.5 times faster than existing transfer learning-based approach. It also provides stable online policy serving performance with less than 3.6% reward degradation. It helps achieve 47% and 32% higher CPU and memory utilization while reducing SLO violations by a factor of close to 17 times during initial policy training. On the limitation side, meta-learning does not guarantee adaptation in out-of-distribution cases, which might be mitigated with detection and fine-grained customization. This might happen rarely in cloud data centers, as the training data might already include diverse application sets. And in our future work, we're looking at to extend this meta-learning based framework for other workload-aware machine learning for systems cases as a general paradigm, which facilitates fast model adaptation. And thank you.